Okay, so we'll start today's session. Welcome to live session 7. Uh, Today, what we will do, we will discuss about something on something on gas welding or oxyacetylene gas welding. To be more particular, we will talk about different kinds of flames all over again, uh, like uh, like those carbonizing flame, oxidizing flame, neutral flame. Uh, when you should go for which kind of flame, for which material it should be used, those stuffs. Then we will discuss something on shielded metal arc welding. So basically, we will cover different kinds of welding as such, where we will cover gas welding, shielded metal arc welding, and gas tungsten arc welding as covered by professor in your earlier week, right? So let us start. So we will again initially talk about this gas welding all over again. Uh, to have some overview of that oxyacetylene welding, right? So, like like an arc welding in gas welding also, uh, this is a process where you are melting and joining metals by hitting them with a flame, right? So the heat source is the uh, flame due to chemical reaction between two gases, right? Those two gases can be oxygen and some kind of fuel gas. It kind of acetylene, it kind of hydrogen, it kind of methane, propane, it can be anything, right? And depending on the exothermic reaction between those two gases, the temperature it releases, depending on that, uh, we basically generate heat and melt the material, right? Yeah. So gas welding process is most commonly used because of its high flame temperature. Uh, the oxyacetylene one, right? So oxyacetylene one is the most commonly used gas welding process because of its high flame temperature. So in terms of different kinds of flames, what we had talked, so we had three different kinds of flames, right? So we had, so if we talk about different kinds of flames, so let me take black. So what are my three different kinds of flames? We have neutral flame, we have oxidizing flame, and we have reducing flame or carbonizing flame, right? So these are my three different flames in oxyacetylene gas welding. Now coming to this neutral flame part, uh, this refers to the case where oxygen and acetylene are mixed in equal amounts, right? So the ratio of oxygen and acetylene by which it will be mixed up, that will be 1 is to 1. And that is burned at the tip of the welding torch, right? So how can you define, or by looking at the flame, how can you understand that yes, this is a neutral flame? So a neutral flame is characterized by a short inner core. So if we talk about neutral flame, how can you define? You have a short inner core, right? Then what you have? You have a longer outer envelope. So by looking at those two characters of the flame, or even we can see the color of your flame by which you can identify that yes, this is my neutral flame. So the inner core is the area where this primary combustion takes place that I have talked in my earlier video also. So in the inner core, you will have those primary combustions and chemical reactions between oxygen and acetylene, right? And the heat of this reaction accounts for about two-thirds of the total heat generated. So the maximum amount of heat generated in the inner core. Now products of these primary combustions are what? So depending on this chemical reaction of oxygen and acetylene, you produce carbon monoxide and hydrogen, right? That react with oxygen from the surrounding of the air also, and it forms carbon dioxide and vapor, right? So those are the chemical reactions. I will write it down, and then this formation of carbon monoxide and this vapor is the secondary combustion. The primary combustion, because of primary combustion, always carbon monoxide uh, generates, right? Carbon monoxide and hydrogen, and two-thirds of the heat is generated over there. Now, uh, because of the secondary combustion, one-third of the total heat generated in the this outer envelope, right? Now, if we try to draw some schematic uh, in terms of understand that what are those chemical reactions, let me draw some schematic. So let's see, this will be like food, and I will generate some flame like this, right? And this is my inner, so this is my inner core, and this is my outer envelope. So what I was talking is in the primary combustion, during the primary combustion, when this two-third of the total heat is getting generated, what will happen? What is the reaction is my acetylene will react with oxygen and it forms carbon monoxide and hydrogen. This is the primary combustion which is taking place in the inner core part. So the maximum temperature you can generate, it will be somewhere around 2800 to 3500 degrees C. And in the outer envelope, during the during the secondary combustion, where my one-third of the total heat gets generated, what will be my chemical reaction? So here my carbon monoxide will take oxygen from the air, extra oxygen from the air, and it will generate CO2, and hydrogen will react with oxygen to form vapor, right? That is my secondary combustion, and you can see that in the outer envelope, the flame temperature reaches somewhere around 20 2000 to 2500 degrees C, which is lower than this inner core temperature, right? So those are the reactions which is taking place. Now, I was talking about this neutral flame. Now, if we come to this reducing flame, there you uh, there you apply excess amount of acetylene, right? So because of excess amount of acetylene, the resulting flame is called a reducing flame. So here the combustion of acetylene is incomplete in nature, right? So the complete combustion doesn't take place during this reducing flame. And how can you characterize this reducing flame by looking at just at its color? Is it will form some kind of greenish kind of acetylene feather between the inner core and the outer envelope I was talking about, in my earlier lecture video, right? That's how you can characterize a reducing flame. Now, this flame is reducing in nature and mainly desirable for welding of aluminum alloys, right? So, because aluminum can oxidize very easily, you cannot use oxidizing flame during that time, it can easily can react with oxygen and form aluminum oxide, which is not beneficial for welding of aluminum, right? And reducing flame is also good for welding of high carbon steels, right? So I call it also, we call it also carbonizing flame, right? Because excess oxygen can oxidize carbon and form carbon monoxide gas, and porosity can form. Because of those things, people use this reducing flame for high carbon steels. Now coming to this oxidizing flame, here you apply excess amount of oxygen, right? Whenever you apply excess amount of oxygen, uh, the flame becomes oxidizing because of presence of this unconsumed oxygen, right? And these kind of flame will be very luminous, bright in nature, and there will be a very short white inner core, by which you can identify that this is oxidizing flame. Also, uh, just by hearing the sound of the flame which is coming out of that nozzle, you can also understand that what kind of flame you are generating. And oxidizing flame is generally preferred when welding of brass kind of material, because if it forms copper oxide, it covers the weld pool and thus prevents uh, zinc from evaporating from the weld pool. So I just need to mention when you should apply oxidizing flame. So I will use oxidizing flame for brass material because copper oxide covers weld pool and prevents zinc from evaporating from the weld pool, right? So that is when you will use this oxidizing flame as such. Now, I'm not going into the detail of this welding setup all over again, which I already explained in my earlier lecture, right? So we had those oxygen cylinder, acetylene cylinder, we had those bulbs, we had those gas hose pipes through which gas will be flowing. Then you will have some mixing chamber where you will mix those two gases at some specific ratio, and then you'll have those welding torch, right? We also talked about this explosiveness of acetylene, right? So acetylene becomes violently explosive even in the absence of oxygen, right? So that is why acetylene is dissolved in acetone. That's how it kept in the cylinder. And yeah, so I will mention it as a note. So C2H2 is violently explosive and dissolved into acetone to keep it in the cylinder. Okay, so these were something which we discussed in terms of oxyacetylene flame, right? Then there is something called oxyhydrogen combustion also. So in place of acetylene, you are using hydrogen. Uh, you are choosing hydrogen for your reaction to take place with oxygen, right? Now, complete combustion of hydrogen that requires oxygen to hydrogen ratio of 1 is to 2. So in the ratio of 1 is to 2, if I react with hydrogen and oxygen, form some vapor formation, right? So these gas mixture produces a kind of strongly oxidizing flame where you can generate your temperature till some 2750 degrees C. So I can increase my temperature up to this temperature. However, it is impossible to obtain a neutral flame in your oxyhydrogen combustion uh, just by some visual methods of flame adjustment, as we were explaining during this oxyacetylene flame, right? So oxyhydrogen flame itself is visible, and there you cannot distinguish any kind of combustion zone over there. So I will mention that as this is visible. And sorry, no combustion zones are distinguishable, right? Yeah. In terms of basic features of this oxyhydrogen combustion, uh, what we can do is if we want to avoid some oxidizing flame, you can set your pressure regulator in such a way that you will increase your amount of hydrogen over there, right? So when you are increasing your amount of hydrogen, that time your flame will be reducing in nature, but not carburizing. That keep it in your mind. So we call it reducing flame when you are using hydrogen in excess manner. Now, in reducing flame, the temperature will be some several hundred degrees lower than that of neutral flame when it is, right. And when should we use oxyhydrogen flame? So oxyhydrogen flame is mainly used for welding of aluminum alloys, or if you want to weld some low melting temperature like lead. So aluminum alloys and lead lead can be useful by oxyhydrogen flame. What else we have covered in terms of chemical reactions of different gases? So we talked about acetylene, we talked about hydrogen. Then we also covered some combustion of natural gas, right? Natural gas and propane. So how does this chemical reaction happen? So basically, you react methane with oxygen and generate carbon dioxide and vapor. And if it is C3H8, I need to so this will be CH4 plus 2O2 and here 2H2, right? And if it is say 3H8, it will generate 3CO2 plus 4H2. So that is how complete combustion of methane or natural gas and propane does takes place. So this is propane This is methane in terms of combustion of natural gas, right? Now, when the flame temperature is very high, uh, if the flame temperature reaches uh, somewhere around 2700, 2800 degrees C, when it is high enough to weld steel, uh, the flame atmosphere will be excessively oxidizing, right? You have to have uh, generate excess amount of oxygen to increase your temperature to such a high temperature, right? But when the ratio of oxygen to fuel gas is decreased to produce a carburizing condition, the flame temperature will be somewhere around 2500 degrees, as I was talking about. But that temperature is not suitable to weld your steel material. So over here, uh, during this combustion of natural gases, what I mentioned, it's I mentioned over here. I will keep it as a note. Reducing flame is not suitable for welding of steel materials because of generation of lower temperature. Okay, so this is what we talked about the different kinds of chemical reactions between different kinds of gases, right? So why don't we try to answer a few of those questions which covers this part. So in my first question, I asked in oxyhydrogen combustion, complete combustion takes place when oxygen to hydrogen ratio is 2 is to 1. Is it true? So I say oxygen to hydrogen ratio. What was my reaction in oxyhydrogen combustion? I mentioned somewhere, yeah. So this will be two parts of hydrogen with one part of oxygen. So oxygen to hydrogen ratio should be 1 is to 2, right? So this is a false statement over here. Then I say that complete combustion takes place when it produces neutral flame, when it produces oxidizing flame, and when the temperature reaches close to 2750 degrees C. So this is also a false statement. So for complete combustion, I need to produce some excess amount of oxygen and I need to generate a bit higher temperature where your flame characteristics will be oxidizing in nature, right? So this is a true statement. This is a true statement. Agreed? Then I ask, which of the following are true? In combustion of natural gases, carburizing flame is ideal to weld steel material. I just mentioned that because of generation of lower temperature, carburizing flame is not ideal to weld steel material. So this is a false statement. Then I asked, oxyhydrogen flame is useful for welding and brazing of aluminum alloys and lead. This is true. Has distinct combustion zone. You cannot distinguish the combustion zones over there in oxyhydrogen flame just the way you do it in oxyacetylene flames, right? So this is also a false statement. So B is true over here. I hope these are straightforward questions. We can simply answers. Okay, answers those down. Now, then I will come to this welding method part where either you do a forehand welding or a backhand welding, right? So either it is leftward or rightward in whatever way you will mention. Now, what happens in forehand welding method? So let me draw some. Let's take this space. Draw some schematic. So for forehand welding method, and this is the backhand welding method. Okay. So in my forehand welding method, yes, this is my weld metal. This is the region of weld deposition, and my filler rod will be positioned like this, which is inclined in some, let's say, 30 degree. So it can vary in between 30 to 40 degree. And then my welding torch also will be inclined in some 60 to 70 degree, like this way. And my welding direction is this direction. So this is my welding direction. So 60 to 70 degree, right? And how will it look like in backhand welding method? In backhand welding method, this is my weld position zone where my feelers are inclined. So let's say this is my feeler rod. This is somewhere inclined as 50 degree, and my welding torch will also inclined like this. And so this is my welding torch, which is inclined at somewhere at 40 to 50 degree, and this is my welding direction. This is my welding direction, right? So in the backhand welding method, welding begins at the left hand end and it proceeds towards right. Hence the name is we call it rightward technique also. The vice versa is for forehand. This is rightward technique, correct? So when we should use backhand welding method, when we should use forehand welding method. So if you see this backhand welding method, uh, my flame is constantly directed on the edge of this constantly directed on the edge of this V ahead of the weld puddle, right? There will be no sideward motion of that weld puddle, which will be necessary like the way it is required in your forehand welding method. And mainly this is used for heavier or thicker base metals, right? Here your weld penetration will be higher, and mostly this is used for thick metals. And you don't need to use any kind of uh, what should I say, some bevel formation to uh, feel those gaps, right? So this technique involves lower cost of welding than the leftward technique, right? In the leftward, uh, the feeler rod when it is used, that is directed towards the welded part of the joint, right? And and my flame is pointed in the direction of welding, so it basically preheat the edge of the joint. In the forehand, it basically preheat edge of the joint, which is not the case for this backhand or rightward one, right? Uh, However, in leftward welding method, you will have those good control and good appearance of the weld characteristics, and this is mainly used for thin sheet welding. However, if you want to go beyond some thickness of 3 mm, you have to bevel those plate edges, right? Uh, there will be some included angle. We have discussed about this bevel edge preparation, right? So that there will be this root fusion will be very good over there whenever you prepare it as a bevel edge, right? So for thicker sections demand bevel edge preparation, so that the root fusion will be achieved over there, right? And if the material is too thick, if it is more than 6 mm, it is very difficult to obtain even penetration at the bottom of that V, and the quality decreases basically as the plate thickness increases in your forehand welding, which is not the case for backhand. So backhand is mainly used for thicker sections, forehand is mainly used for thinner sections, right? Okay. Hmm. So I have asked that backhand welding method is sorry, there is a typo. Backhand welding method is used to weld thick metals. Weld penetration is less. To weld thin plates, weld penetration beforehand is required to join thick plates. So backhand welding method is used to weld thick metals. This is true. Here my weld penetration also will be higher, right? This is a false statement. This is also a false statement. Forehand welding method is used to weld thin plates, and here I have mentioned as weld preparation beforehand is required to join thick plates for backhand. This is also a false statement that is required for forehand one. Okay, so A is correct over here. Then we will move to different kinds of electrodes which are used in your shielded metal arc welding, right? And before that, in terms of just to conclude that gas welding part, what is my advantage? What is my disadvantage of using gas flames as a heat source? The main advantage of oxyacetylene welding process is that your equipment is very simple, it is portable, it is inexpensive, so it is convenient for maintenance and repair application, right? However, you will have limited power density, or you have limited source of heat generation, and also in gas welding, your welding speed will be very low, and the total heat input per unit length of the weld will be rather high, resulting in large heat affected zones, right? We have talked about your heat affected zone should be optimized in such a way that weld joint strength that also that should be in acceptable range, right? If your heat affected zone is very high, there will be severe distortion of your weld metal, and those aspects are there. So, so basically, oxyacetylene, or we say it oxyacetylene because that is generally used in gas welding. So, oxyacetylene welding is not recommended for welding of reactive metals, right? Such as titanium or zirconium. So, those kind of metals are reactive in nature, right? So, for those reactive metals, that time oxyacetylene is should not be used. Okay. Then we will move to, as I was talking about, Uh, we'll move to this shielded metal arc welding, right? Till now, do you have any question? If not, we'll move to this shielded metal. Okay, so in shielded metal arc welding, uh, as I was talking about in gas welding, your heating source is the flame. Here, my heat source is the generation of arc, right? Which will be established between a stick-like, uh, it will be flux-covered electrode and the metals, right? The arc will be established between the metal and the covered electrode. So, if I want to, uh, let me draw some schematic first. So, let's say this is my electrode. This is looking something like this, and these are my flux covering at those two ends. So that is my flux covering. This is my core wire of that electrode. This is my arc, which will be established between electrode and the workpiece. Let's see this is. So this is my arc. Huh? This is looking something like this. Something like this. And there will be some shielding of gases. Gas shielding. We have some droplets, right? We have covered those mechanisms of droplets formation, right? You will have metal droplets, you have flux droplets, you will have different kinds of droplets from the electrode, right? So it is also called stick welding. So the electrode holder is connected through a welding cable to one terminal of your power source, right? And the workpiece will be connected through a second cable to the other terminal of the power source, right? There will be positive and negative. Either I will connect my electrode to positive, depending on your polarity, right? We talked about this DC, P, DC, and straight and reverse polarity. Okay? We'll again cover that part also, right? It is the very fundamental part of this shielded metal arc welding, as you know. So the core of this cover electrode, what we are calling it as core wire, that conducts my electric current to the arc and it provides the filler metal for the joint, right? So your electrode can be consumable or non-consumable depending on it. You can use your filler wire, external filler wire, or you cannot. Now, yeah. Now uh, for electrical contact, the top of this core wire is bare and held by some kind of electrode holder. They'll have some kind of electrode holder which will hold my electrode wire. Right? Now, the electrode holder should be essentially a metal clamp with an electrically insulated outside shell, right? For the welder to hold it safely, right? Now, the heat of the arc that causes both the core wear and the flux that is covering your electrode tip that will be melt off as droplets, right? And the molten metal collects in the weld pool and then it solidifies in the weld metal, right? That is how it works. Now, what is the functions of those electrode covering? It will provide me some kind of protection. So it provides some gaseous shield to protect the molten metal from air, right? So then comes the picture of different kinds of electrodes. So we talked about, or we have covered the cellulose electrodes, then butyl electrode, then basic electrode, then metal powder electrodes. Those different kinds of electrodes are there. So, let's say these are my four different electrodes, what we know as of now. Now, for cellulose type electrode, the covering contains cellulose. So, what is cellulose? It's C6H10O5. So, this is my chemical formula of cellulose. Now, there will be a large volume of gas mixture of hydrogen. It will cover carbon monoxide, it will cover vapor, it will cover CO2. Those will be produced when cellulose in the electrode covering, and that is heated, and basically it will be decomposed into these components, right? There will be hydrogen, carbon monoxide, vapor, carbon dioxide, right? Uh, there is some kind of electrode called limestone type electrode also. So we call it limestone electrode. So this is CaCO3, right? That type of electrode, on the other hand, it will generate CO2 gas and calcium oxide slag form when the limestone decomposes, right? Now, this limestone type electrode is a low hydrogen type electrode because it produces gaseous field low in hydrogen, and it is often used for welding metals that are susceptible to hydrogen cracking. So, which kind of material is very susceptible to your hydrogen cracking? It's steel material. So, if we talk about high strength steel, that is very prone to your hydrogen cracking. So, steel material is prone to hydrogen cracking. And during that time, I need to use this limestone type electrode. And then what else do we have? We have something called rutile coating, right? We have something called rutile coating. Um, the rutile coating is mainly is containing titanium oxide. So rutile coating is composing of titanium oxide. Now, what is there in rutile coating? What is there in rutile coating? It basically high proportion of titanium oxide will be there in coating. Um, Titanium oxide basically what it does is it promotes our ignition, it promotes smoother cooperation, scatter will be less with titanium oxide, and because of rutile and the ionizers are there in the coating. Those electrodes can be used with both the polarity, both the straight and reverse polarity. We can use rutile electrodes, right? And they are specially suitable for fillet welding. So those are some characteristics of rutile electrodes. Let us write down. So for cellulose one, what we have? We have deep penetration is possible. Hi Kajal, PDF of what? Can you please elaborate? This is suitable for vertical welding, then hydrogen generated, sorry, risk of cracking in heat affected stone. Right? Those are my cellulose electrode characteristics. And in rutile, we have good bead appearance. Because of presence of titanium oxide, the slag will be viscous in nature. There will be viscous slag. So because this is viscous, the slag removal will be very easy over here. Easy slag removal. Those are some those are some characteristics of rutile electrode, right? Then let us talk something on this basic electrode. So there is something called basic electrode where those electrodes are used for some high quality application, welding of um, some steel materials where your electrode should be stored in some portable dryers, right? Because to prevent your electrode from moisture absorption, right? They should be carefully stored and dried. Uh, so I have basic electrode also. Let us write down over here. So basic electrode. What are some of the characteristics of basic electrode? Maybe we can refer it as my limestone electrode also, because this is also, we call it low hydrogen electrode. Okay. So these are my low hydrogen electrodes. Just a minute, huh? These are my low hydrogen electrodes. This will be more fluidic or more viscous than the rutile coating. However, slag is of fast freezing type, right? It will cool down very fast. Your slag. So what I was talking about, this easy removal of the slag for rutile coating, that is not the case for basic electrode where your hydrogen content is less. However, uh, the viscosity or fluidic nature is more than its when you will compare it with the rutile one, right? Now, Uh, because we call it a low hydrogen electrode, as I was talking, you should keep it in a low moisture content, right? Uh, to prevent it from the moisture absorption, uh, it should be carefully stored and it should be carefully dried with some portable dryer, right? And those eliminates the possibility of moisture absorption, right? Then also you have those metal powder electrodes. So you also have metal powder electrodes. What we have in metal powder electrodes, because of its powder nature, my deposition rate will be very high over here. So high deposition rates can be achieved by increasing, if you're increasing your iron powder content in your flux coating, you can increase your deposition rate, right? And higher deposition rate is not only achieved because of addition of metals in the flux, but also uh, it can carry more current for the same core wire diameter because you are increasing iron powder, right? It can carry more amount of current, uh, and because of that also your deposition rate will be higher. So higher deposition rate because of increased iron content and ability to carry more amount of current, right? So those are something in terms of this function of electrodes covering, why you should use the function, what type of electrodes you should use in terms of protection of your molten metal, right? Now, what else it serves? So my electrode covering, what we have, it provides those gaseous shell to protect my molten metal. What else? The purpose it serves. It also provides the deoxidizers. So it also provides deoxidizers and fluxing agents to deoxidize and clean your weld metal, right? The solid slag which formed, that also protects the already hi Kajal. I just wanted to know what PDF you were talking about. Uh, Are you talking about the one which I am discussing right now? Am I audible? I was just confirming. Are you talking about this one, what I am discussing right now? If it is so, then I am sharing it after each and every lecture. The NPTEL team must be sharing the link where I have already uploading all those PDFs with those questions and with those discussions. And also, I'm sharing uh, the videos also. You can go through the videos, right? Okay. So it also, Okay, let me